This is the start of our section now, 3.2, where we use a lot of rules to do the derivatives. We're not going to use the limit process as in section 3.1. We have had the benefit now of lots of mathematicians over hundreds of years doing derivatives with the limit process and observing some rules. So let's jump right into them. The first one is called a constant rule, and we know what a constant is. A constant is just a single value. What we have here in our notation, this is one of those other notations. This is equivalent to the notation dy dx. Remember, this would be expressing that y is the output and y is some constant c. Or we could say that it is f prime of x, where f of x is equal to c. Now a specific example would be, let's say y is equal to 5. We know that that would be just a horizontal line up here at 5. And if we look at, remember the derivative is the slope of the line tangent to the curve. It doesn't look like a curve, but we will call that a curve at a point. And so we want to know what is the slope of that line, and of course our slope is 0. Hence, we look at this and we have that the derivative of our function with respect to our input variable x, the slope is equal to 0. The same discussion is going to be used with these problems as we've been using. Okay, so we go on. And if we look at if n is a real number, then f of x equals x to the n is differentiable. Remember, differentiable means that the function has a derivative. We have this happening, then f of x equals x to the n, and we have this. Now what we're looking at is, suppose that y is equal to x squared. Then our derivative with respect to x, the derivative of our function with respect to x, would be, and what I'd like to explain is actually what comes down here in the constant multiple rule, is that we have, this is equivalent to 1 times x squared. So our coefficient is 1, multiply the exponent times the coefficient, and then subtract 1 from the exponent. So our derivative would be 2x. Now remember, this is another function. So this is saying that we are able now to find the slope of any line on the curve, the x squared curve, by using this formula. So if we want to find the derivative, find the slope of the tangent, on this function at x equaling 3, then we would have dy dx. I'm going to use this vertical line here such that, or with the case that x is equal to 3, would be then 2 times 3, or 6. Now let's go to our inspires, and let's just kind of verify that. Use a new document, and let's add a graph, and we're going to actually graph the function x squared. Now we've been through this before, so I'm going to just move through the actions here. I'm going to come in and place a point. I'm going to place a point somewhere around in this vicinity. I'm going to change the coordinates of this point. We said at 3. And of course I've lost my point, but I'm just going to grab the screen. This is a grab and drag. I'll just grab the screen and bring it down here. I'm going to place a tangent at this point. We've been through this. I feel confident that you can do the same thing. And I'll just extend that. Let's see if I can extend it. There we go. Then we'll come in here and we'll measure the slope of that line, and the slope happens to be 6. Now again, if I look at the derivative of this, it would be, let's go back to the notes here. I take the exponent times the leading coefficient, so this would be 1 in this case. So n times 1 is n, and then subtract 1. And so the derivative function is 2x. If I wanted to find this at another point, then I would have the ability to do that. So that leads us right into then our constant multiple rule. If the function is differentiable and c is a number, then c times f, we also call that a scalar. So we put the word scalar up here. Okay. Scalar is also differentiable. And so we're doing the exact same thing as I've shown you on that page. Okay, so let's go on. We'll just try this on this problem. Before I start though, I'm going to have to write the function g of x in a more usable way. And this is where all that worked in Algebra 1, where we convert the radical into a fractional exponent. It's going to help us. So now if I want to find the derivative of g of x, my rule is that I take the leading coefficient, which is 1, even though it's not written here, this leading coefficient, times the exponent, and then I subtract 1 from the exponent. So I would have 1/6 x to the negative 5/6 power. Now, although that's a sufficient answer, the rule is going to be always write your answer with positive exponents. Okay. Another rule that I'm going to ask you to do on all of your homework, and if I look at your homework, I want to see this, even for those of you who know what to do, because since I do not know who that is when I'm grading papers, I want you to show me, show me this process. In other words, show me that you've multiplied the leading coefficient times the exponent, and that you've actually subtracted 1 from the exponent. Okay, going on then, our answer would be 1 divided by 6 times x to the 5/6 power. There's no need to rationalize that. You could, if you wanted to, convert that into a radical, but it would not be necessary. Okay, let's look then at the Inspire, and let's see what we would need to do to get the same answer from the Inspire. We know about the symbols palette, or excuse me, the template palette, and we can use our derivative from that. On the click pad, again, it's control on the multiplication. If you're on the touchpad, you have your own little key right here. We have to put in our variable, our input variable, tab, and then our function, which is the 6th root of x. So if we look for the 6th root of x, if you go have control on the exponent key, you can actually have that. You don't have to convert it to x to the 1/6 power. And when we press enter, we get the same answer that we had over here. So you can check every single one of your answers. Now, do not lose sight of this. This function let's say function's output is the slope of a line tangent to the curve at a point. It's the same definition of a derivative that we've been looking at. So the function's output is a derivative. We can then go back and input anything we want in here and locate the slope of the line tangent to the curve at any specific point. Okay, well, let's go on and let's look at this problem. Here is where we've got now actually three terms, and in order to find the derivative of this, we're just going to take the derivative of each of these terms and then combine them all together. So again, I want to see your work, so this would start by saying 2 times 3 times x to the 3 minus 1 minus 4 times 2 x to the 2 minus 1 plus 3 times 1 x to the 1 minus 1. Remember, even though we don't see it, it has an exponent of 1 up there. Okay, so we'd have 6x squared minus 8x plus 3, and here I'm going to put 0 there just for the matter of conversation. What is x to the 0 power? And I'm sure most of you will recall that that's equal to 1. Remember, the exponent tells us how many times we use the base as a factor. We're not going to use any, and so 1 is a factor of everything. And so we will end up with just 6x squared minus 8x plus 3. Go back and review. What does this tell us? And again, it's telling us this right here. That is a function that is going to allow us to find the slope of a line tangent to this curve at any point. We just need to know what point we're going to use. Let's go on. Things getting to look a little more complicated. However, let's break this apart. This could be pi divided by, and we can square this, 25x squared. Now, we haven't talked anything about having the input, the expression in the denominator, so I'm going to write this as pi, remember pi is a constant value, pi divided by 25 x to the negative 2. Some of you might know that there's something called a quotient rule, but we're not going to have to get into that at this point. So now, if I want to find the derivative, and again, dy dx is our notation indicating that we are going to look at our derivative, we take our coefficient times our exponent, and then remember, we're always subtracting 1 from the exponent. So we end up with negative 2 pi divided by 25 x to the negative 3. Again, remember, I want to have all positive exponents on the variable, so we'd have negative 2 pi divided by 25x cubed. Go back and review. What does this tell us? It tells us that this is a function that will yield or has an output that is the slope of a line tangent to this curve at any point. All I need to know is at what point are we going to evaluate this.